Yeah, so yeah, we're gonna talk about multi-layer perceptrons for 40 to 45 minutes. So we're trying to understand width, width, width. I don't know. So, trying to understand width and an MLP because we're coming from a context of we made this observation where if you have a standard MLP, like with, like this thing, that's like a standard, except that should be like a 10H, but the observation is that a single layer can move any input point to any other input point, like it can overlap them. And so you can implement any Boolean function by each layer maps, like a +1 output. Like the Boolean function is partitioning the two inputs, the set of inputs into two classes given by the output label, and so like you just collapse all of those points into a single point, and then you can always separate like a single point with a hyperplane. So we implemented that. We implemented that, like, so this manually, this is like the thing that does that. It just, it selects, right, okay, so like these are all the positive inputs, and then it's saying, like, you just overlap two of them, like you randomly select two points, and then you create a layer that overlaps them, and then you add that layer to the neural net, and then you do it for the negatives. You don't strictly have to do it for the negatives, but we did. And so then you have like an exponentially large neural net that computes an arbitrary Boolean function. So like it's exponentially deep, exponential number of layers. I mean, it actually depends on the size of the, two classes. And so anyway, like you can hand construct a neural net in this way. And so the thing is the width of the layers is like equal to the input dimension. And also, by the way, this like so like this is a 10-dimensional function, and it's like these are all the inputs, and these are the activations at the final layer. So basically, it's just showing that there's like two types of row. Yeah. So like presumably these ones are like the +1 outputs, and the other ones are the -1 outputs. So anyway, yeah, like this gives you, neural nets, MLPs that are also another observation. Yeah, like another observation is that the order of the layers. Well, no, I was gonna say like it doesn't matter. That's not strictly true though, because yeah. But anyway, all of the layers have, width equal to n for n-dimensional inputs. And, and then in the worst case, and even the average case, like over random Boolean functions, you're going to have like an exponent. It's going to be exponentially deep. And so we're kind of trying to figure out, like, what if we don't want it to be exponentially deep? Now, I think it is the case, like, if you're talking about random Boolean functions, like there's there's a basic result, like in computer science, where it's like, if you're talking about like Boolean circuits. I mean, we're kind of talking about Boolean circuits, but anyway, no, anyway, most random Boolean functions probably require like exponentially large representation. I mean, obviously depending on your representation scheme, because I mean, like you could always have a representation scheme where like one of your atomic computations is the function that you're trying to represent, and then you have like a size 1 representation. But anyway, we were trying to understand. Yeah, we're just trying to understand like what how does, if you increase like width, how does that help you? Yeah, because right, because we have this thing like where you have like a layer, okay, so it's like a layer, and it's moving a single point. It's moving a point X onto to overlap with a point Y, while keeping all of the other points stationary. And so like it does that by the weight matrix is like starts with the identity matrix, right? That keeps all of the points stationary. And then what it does, so you're going to map x onto y. What that means is that there's some subset of indices where x and y are different. And so it's equivalent to you're going to flip the corresponding bits in x, so that it looks like y. And in a matrix format, that corresponds to like the ith row. Like if you're going to flip the ith bit, you're going to have to modify the ith row in the identity matrix because like the row corresponds to the output. And basically what's going to happen is like the sign pattern of the ith row is like going to resemble x, and then like there's going to be like some cancellations, and also you have to use the bias, and then anyway you end up with this row that is the identity row for every input except for x, and then it flips the it's kind of hard to put into words actually. I mean, like this is where you do it. Yeah, I don't want to explain all that, but right. But anyway, so it's like so yeah, like we're trying to understand, and I mean, yeah, like we're trying to keep the MLP interpretable, right? Like we have like a class of I just described like a class of MLPs. They're eminently interpretable. I mean, not in like a like in a word vector distance sense or whatever, but they're interpretable in the sense that what every layer is doing. It's collapsing these 2 points together, and so like it's super interpretable. And it's just that it's exponentially large, like it has an exponential number of layers, like exponential in the input dimension. So yeah, we're kind of like, can we add more width to like, at least in certain cases, reduce the exponential depth whilst maintaining interpretability. You see what I'm saying? Like that's what we're pondering this fine morning. No, it's like mid-afternoon. So I did just drink a lot of coffee though, so it's kind of like it's the morning. Yeah, okay, so like like I had a little right, we're yeah, so, so like we're just thinking of the thing where you're like like my inputs perhaps are dimension 3. Okay, there's actually this right, I mean there's also this concept of like the amount of computational work that's being done by a layer, and from our perspective that's kind of seems to be like the number of bit flips, like yeah, I mean it seems like if you have n rows, you can flip n bits, like, and you can distribute out those flips over whichever inputs you like. Right, so if you think about like the final destination of all of the inputs, you know, that directly gives you like how many bit flips have to happen. And I mean, also like the final destinations are, you know, like arbitrary, so they can I mean, that's kind of like, you know, that's a thing you could certainly optimize in some way. But anyway, yeah, if you take the final 2 points that you're mapping like all the plus ones onto and all the minus ones onto, yeah, I mean, that directly entails how many bit flips you need for each input to get to the destination point. And yeah, it seems like the an n by n layer, like you have n rows, so you can flip n bits per layer. Although it becomes kind of hairy because like if you partially flip move a point, you have to like the next layer has to remember where it was moved to complete to move it to complete the movement. And there's also like circumstances. Well, yeah, never mind. So anyway, like if you add more width, it's like, I mean, like the first, yeah, I mean, like you're adding more rows, which is equivalent to, I mean, every row you have is an extra bit that you can flip. Yeah. So, but, eh, there's kind of a question of, nah. Yeah. I guess that makes sense. So I mean, like if you go from like 3-dimensional input to 6-dimensional layers, like you should be able to have the number of layers, perhaps, because you're doubling the number of bit flips per layer. I think it would be like, so if you took, So I don't know, it would just be like the first layer would just be like a random, you have like 8 points. And you have these 8 points, and then you're randomly mapping them into 64 points, and then the idea is that it should be easier. What's the thing though? Because like you're adding. Yeah, I mean it might be easier. Yeah. Does that make sense? I don't think that actually makes sense. So that's kind of what we had here. Like this is right. So this would be like three-dimensional identity map, and then you can. Yeah, but that doesn't make sense. Right. So then, like, to map to 6 dimensions, you would just have. Well. Dang, man, is it 40 minutes yet? Like, no. Oh, dang, it's only 25 minutes. Ugh. Yeah, I'm not really seeing how width is helping anything. I mean, it's like, okay, so like if you have the like the yeah, if you have like the neural net setup going here, like yeah, we're like working with this interpretation where, you know, like each of these hidden units, like these are the inputs. Yeah, that's also kind of, yeah, so, I mean, if you just have these three units, you ignore the fourth one, well, then it's basically saying, you know, like each of these in the weights, they are selecting, you know, possibly the same. I should just use don't use plus, just use vertical dash or one. Anyway, so like what this is saying is that like this point or like this activation is going to be equal to or what we're assuming is that it's going to be equal to x0 unless the input is a specific input and then it flips the x0. Because, yeah, I mean, like in the matrix, it would be like, I mean, like the matrix for that layer would be like, you know, like this is H0, H1, H2. This is like the outputs. And, so, yeah, like, it would be something like, -1, 1, and then the bias would be, like in this case, 1, I think. So like, maybe this should be a 2? Maybe it should be a 2. So like when you have, 1 negative, these become -2 and they go to 0. So like, yeah, except it should be the other way. So you get a +2 here and then -2 here, so these go to 0. Then you get and then the bias just becomes the output, so it's a 1. So like it's successfully flipped that bit, but like on any other input, like these are going to cancel to 0, and then whatever the sign on the 2 is will dominate. And so then it's just equivalent to like the identity row. Yeah. So it's kind of like, I mean, like if you add an H3, you know, then like you're just extending this matrix by a row. Which means like you can like, I mean, from the matrix perspective, like you can choose another input to flip a bit, but it's not actually clear what bit would be flipped. Although if you just stay in 4 dimensions, then it's like, then it would, you know, that doesn't make it any more, like, clear. It's like I have to maintain interpretability, man, you know, like, because the thing with, like, you know, if you go to a higher dimension, it's like, you have more rows in the matrix, so you can flip more bits per layer. But, like, you also have more bits that possibly need to be flipped. So it seems like from that perspective, like, it's not clear that, it's not clear that, yeah. I mean, there's the observation that, I guess, like, in higher dimensions, you're going to have, like, vacant spots on the hypercube. Like, if you're going from 3 dimensions to, like, 6 dimensions, that means you have 2 power 3, 8 active points, and then you go to, like, 64 active points, so you'll have, like, empty places. Yeah, it might be helpful from the perspective of, I mean, like, one way to optimize the, yeah, I don't like one way to optimize this construction algorithm, right? Because, like, we're literally just picking random x and y, and then we're mapping x onto y, where x and y have the same output label. It would probably make sense to you could probably calculate, I think you could calculate for each class +1 inputs, -1 inputs, It seems like you could like calculate its like yeah, I mean you could okay, so you take all of those points and then for each column you just take the majority and then that will be like your binary mean, which yeah would like minimize the number of bit flips for that set. But if you go to high dimension, would that, or like a higher dimension, would that? I'm not seeing how width. I'm not seeing how width is like helping us. I mean, like it obviously does because if you know, like when people train MLPs, they have like not a lot of layers and they have a lot of width, and then like it seems to work. Of course, you know, like people don't spend a lot of time training like random Boolean functions, but yeah. We'll see. Are we at 45 minutes, guys? I'm doing Pomodoro. Oh man, I got like 7 more minutes. Dang, dude. Let's see. I get any chats? Probably not. I'll check chat, dude. Yeah, no. There's no chats. Sweet. Yeah. I mean, like, could you just maintain like 2 parallel thingies? Cause yeah, I mean, you can maintain 2 parallel thingies, but then I don't know how you would recombine them. Okay, yeah, let's I guess look at that real fast. Or like maybe you wouldn't have to recombine them. I don't know. So it's 1, it's 2, it's 3, it's 4, it's 5. Okay, so we're saying like we have you know, like you put in like, you know, like 1 0 1 as the input, and then maybe this one maps it to like 0 1 1, but this one keep like this, right? So like yeah, and so what you want is I mean, like if you have like this, you want this one to be like the canonical branch, like for this input. So like each input has one canonical branch, and the other branch just gives the identity. So could you? So if you had that, you could flip you know, you could double the flips, or like, I mean, you know, and you could add on more branches. So you could do like a lot of, I guess, like parallel computation in a single layer. The problem though is that you have to maintain interpretability. It's like, how would you maintain interpretability like at the next layer? That's the problem. Oh no, that's a terrible color. Let's make it hot pink. That's way better. It's 6, it's 7, it's 9, it's 10. I mean, what would you want at the next layer? Because you're saying like, because what we're saying is, you know, like for this particular input, we're starting here, and then the correct mapping is this branch. Although this, you know, so like this branch is doing mappings for other inputs, but not 101. So it doesn't do anything to 101. So it just keeps it where it is. So then it's like, it's like, that's cool, but then, yeah, like what does the pink layer do? Because, yeah, I mean, like for some inputs, it has, yeah, I mean like the inputs cannot, yeah. Dang, man. Are we at 45 yet? Oh, dude, we're at 45. Okay. Let's Pomodoro, guys. I gotta do Pomodoro. That was a roughie.